Back to share screen. All right, so now we're recording, I hope. If not, I'll just replay it all and do it myself. We're talking about periodic table. I'm sorry I didn't get recording started at the beginning for Piper if she's just getting in on this. But electronegativity is how attractive atoms are. And this becomes important when you have a bond because this how attractive are the electrons. Fluorine is the sexiest. He wants the electrons the most, meaning that if francium has one electron and he meets fluorine, fluorine's going to take that electron away and there's not going to be any sharing at all. So it's a ionic bond. But if you have two elements that are close together in the periodic table, they're going to share more equally. So if the electron doesn't get completely taken away from one, instead of being an ionic bond, that's a covalent bond. So electronegativity really defines ionic and covalent bonding. All right. So that's the first thing we need to know about the periodic table. The second thing would be ionization energy. Definition of ionization energy is how easy is it for that electron to be given away. It is going to be very easy for fluorine to give his electron away. So the bigger something is, the easier it is to get rid of that electron. So ionization energy is opposite of electronegativity. Ionization energy increase, no, it's easy. Okay, it's backwards. I did it backwards. Ionization energy is the same relationship because if an atom wants to get rid of an electron, it's going to have low ionization energy. If an atom doesn't want to get rid of electrons, in other words, it's very attractive, it's going to be a high ionization energy. So ionization energy, electronegativity, same thing. On the final, it's going to ask you about first ionization energy. That just means the energy it takes for something to get rid of its electron, okay? And if you stop and think about what it means, ionization is, can it get rid of an electron? Electronegativity is it going to attract the electron? You can kind of put that together. The third relationship is radius. This is the one that is opposite. Francium has the biggest radius. Let me find a different color for that. Francium has the biggest radius. Technically, helium would have the smallest radius. But the radius increases as you go down because you put a new shell on. The radius increases as you go across because, no, it decreases as you go across. Oops. It's opposite. It decreases as you go across because as you go across, there's more protons and they pull in harder, and so they make that radius shrink. Okay? So our three relationships. Radius gets bigger as you go down and smaller as you go across. Ionization energy gets larger as you go up because the radius is smaller, and increases as you go across because the radius is smaller. And electronegativity is that same relationship. Okay, so questions about that, because I just kind of goofed it up in the middle. Nobody has a question? Everybody's good? All right. You good? Okay, so next on the list is ionic compounds. We just talked about ionic compounds and electrons. You've got the electrons completely given away, which gives you a cation and an anion. And they are held together by that attraction, just like if you take something out of the dryer and you find that your underwear is stuck to the inside of your jeans leg because of static electricity. That's what's holding an ionic bond together, is basically that static electricity force. Okay? The rule of ionic compounds is that the charge has to equal 0. So you have to balance these out, and I say balancing, not balance the equation, but you have to make sure that you have enough positive charge and enough negative charge that they add up to 0. All right? And you guys, I feel like, knew naming pretty well on ionic compounds, but to remind you, ionic compounds, we don't use prefixes, but we do use Roman numerals to indicate the cation charge. And that is for transition metals, in like lead and tin. The cations in families 1, 2, and 3 are always going to be either +1, +2, or +3. The anions in 6, 7, 8 are going to be -3, -3, -2, -1. 6, 5, 6, 7, -3, -2, -1. And those won't change. But those transition metals up here in the middle, these guys are what we call multivalent, meaning they can have either +2 or +3. So we use Roman numeral to indicate the charge. So if I have this guy and I have this guy, what first we have to do is figure out what the anion is. Oxygen is a -2, so that means that iron has to be a +2. So his name is iron 2 oxide. This guy, we have 3 -2s, which is a -6. So this guy has to add up to -6. So he must be a +3, iron 3 oxide. Do not make the mistake of looking at this and calling that iron 2 because it has a little 2. And again, I feel like you three have got a pretty good understanding of that. So just don't get caught in that. And I don't even think there's anything that asks you how to name an ionic compound. I don't remember. All right, let's talk about solubility with ionic compounds. I should have a solubility chart on here. Solubility chart, of course, tells us, let me find one. Maybe. No, because I always just have a copy of it. I guess I should ask this. Do you guys feel comfortable reading a solubility chart?
Yes.
Okay.
Yeah.
Okay. Brooklyn?
Yeah.
Okay. Well, then I'm not going to waste time and find it. Solubility chart. So you got to read the solubility chart. When you put two ions together, for instance, if we put no, those aren't going to be soluble. Here, we'll do this. FeCl3, iron 3 chloride. And we mix it with silver nitrate. Okay. What's going to happen to these when they get into the solution? First thing that's going to happen is they're going to dissociate. So you're going to have Fe3 plus 3 chlorides plus a silver plus a nitrate. And they're going to be swimming around in there. Am I still on screen sharing? Guys?
Yeah.
Okay. I lost your picture, so I don't know what happened to you. So these guys are all swimming around in there. We already know that these guys, the water will overcome that attraction and pull them apart. But when silver bumps into the chlorine, it's stronger than the water attraction. So the silver chloride will precipitate out, and you'll still have iron 3 ions and nitrate ions in there. Okay. This is a complete ionic equation. Hopefully you all remember that these guys are called spectator ions because they are the same on both sides. Well, if we remove all of our spectator ions, what we have left is the net ionic equation. Net just simply means the thing that's left after you take out all the extra stuff. Kind of like with the example I gave in class was if you're doing a fundraiser and you buy candy to sell at a basketball game, and when you get done, you have to take the candy price out of what your receipts were, because otherwise you think you made a whole lot more money and you still have to pay for the candy. And that's your net amount once you've taken that candy price out. So net ionic equation, you're basically taking out the spectator ions, okay? When ionic compounds dissolve in water, because they are positively and negatively charged, that allows them to conduct electricity. And compounds that can conduct electricity when they're in a solution are called electrolytes. We took that one step further and we tested Gatorade, didn't we? I think so. Maybe we missed it because of a snow day. I can't remember. But Gatorade, we all know is sold as an electrolyte. That's important because in your body, you have to have those positive and negative ions, because that's how your nerves communicate to the rest of your body. So if you don't have enough of those positive and negative ions, then your body can't talk to itself. And so people that get dehydrated get kind of funky because they're not processing well. They can't send those signals through their bodies. So an electrolyte will conduct electricity. Oh, Teddy, hang on. Teddy wants in. If he's out, he wants in. If he's in, he wants out. Now, we have such thing as strong electrolytes and weak electrolytes. And those we covered when we talked about acids right before Thanksgiving. A strong acid dissociates completely. And a weak acid does not. I didn't spell that right. All right. So strong acids will completely dissociate. Same thing happens with ionic compounds. Some of them dissociate better than others. They will all dissociate to a certain extent. They will all conduct electricity to a certain extent. Okay. All right, let's talk about naming acids. The strong acids, there's 6 of them. Acids always begin with a hydrogen. We have nitric acid, sulfuric acid, which has 2 hydrogens because sulfate's a -2, hydrochloric acid, perchloric acid, which is ClO4. What are my other 2? Hydroiodic and hydrobromic acid. Those are your strong acids. The way we name acids is if it is binary, meaning there's no oxygen in it, we use hydro plus ic. If it is has oxygen in it, if it ends in 8, so no oxygen means it would be ide. Then we just have an ic. 8 changes to ic. And if it would end in ite, it changes to us. Okay, so questions about electrolytes and acids. Nobody? Okay.
Will we have to name the acids?
No, I don't think you had, I don't think there was an acid naming, but you have to know which is a strong acid and which isn't.
Okay.
All right. I will double check that and make sure, and if there you do have to name it, I'll let you know. But I don't think there was a naming one in there. All right, we did solubility, net ionic, we did naming, we did strong versus weak. Now we get to go to the covalent compounds. Covalent compounds. Are also called molecular because they make molecules. Ionic compounds are simply ions joined together. And my little green and blue salt block is the example of an ionic compound. Molecular compounds, now instead of the electrons being, or the ions being attracted to each other, they are no longer ions and they're sharing electrons. So we have to follow the valence shell electron repulsion, electron pair repulsion, the VSEPR theory. We have to follow the VSEPR theory, which says electrons are in pairs, which we already know because we did electron configuration and we know they're always in pairs. The electrons have to be in pairs, and we have to follow the octet rule, which means they need to have 8 around the central atom, but sometimes they can have more because we have to have exceptions to every rule. And hydrogen would only have 2. So what we do, first of all, when we have a compound, we count up our valence electrons. Carbon, I'm gonna scroll back here so don't get dizzy. Carbon is in family 4A, which means carbon has 4 outer shell electrons. Oxygen is in family 6A, which means he has 6 outer shell electrons. So there's 2 oxygens, that's 12. So 4 plus 12 gives us 16. Now we're going to put this together and draw our molecule. First, you draw your stick figure. There's 4 electrons. I've got 16 total, so I've used 1, 2, 3, 4. Now I'm going to put them around the outside. 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16. Okay? So we count. This guy has 8. This guy has 8 because this line axis 2, but carbon here only has 4. So we need more electrons. So we're going to move these electrons. I'm going to move these 2 over, and I'm going to move these 2 over. Now we count, I'll use a highlighter to count, 1, 2, 3, 4, 5, 6, 7, 8. 1, 2, 3, 4, 5, 6, 7, 8. Different color for my carbon. 2, 4, 6, 8. Everybody has 8. Okay. When we look at, when we build these, if we have something that has 4 bonds on it, that is going to be a tetrahedral shape, because the other piece of talking about electrons is the fact that they are going to push each other apart as far as possible. So if you have 4 bond areas total, this is a tetrahedral. If you have 3 bond areas and 1 lone pair, this, so we have 3 bonds, 1 lone pair, we still have 4 total bond areas. We still have 4 places for the electrons to be. So this is still tetrahedral for the electrons. The electrons follow that tetrahedral, but the name of the molecule just incorporates this part, and that guy is trigonal pyramidal. All right. If you have 2 bonds and 2 lone pairs, again, we have 4 total places the electrons can be. So we still have this shape, this tetrahedral shape, but now we have what we call a bent molecule. All of these have the electron configuration of tetrahedral. But the molecule in these cases, the molecules are have a different name. In the first case, tetrahedral is the same for both the electron configuration and the molecule, because that has 4 total bonding areas. Okay? If we have 3 bonding areas, stop for a minute and count electrons. 2, 4, 6, right? I'm going to get rid of those. Okay. 6 electrons. That means one of these is going to have to be double bonded somewhere. All right. Let me give you an example. Let's do NO3. Nitrogen has 5 electrons. Each oxygen has 6. 6 times 3 is 18. We have to include that 1 for the -1 charge of the ion. So 18, 19, and 5 is 24. Okay. Nitrogen's going in the middle. There's 1 oxygen, there's 2 oxygens, there's 3 oxygens. 2, 4, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24. Okay? Does everybody have 8 electrons? No. So you have to do a double bond somewhere. So we're going to move these 2 over. Now, 2, 4, 6, 8, 2, 4, 6, 8, 2, 4, 6, 8, 2, 4, 6, 8. Questions about that?
No.
We're good with that? All right. The question that always comes up in class is, does it always have to be this molecule here that's double bonded? No, you can draw this guy like this. You can draw this guy like this. As long as the drawing obeys 8 electrons around everybody, it's okay. And these are all considered to be resonance, which means they shift around. So they shift from this guy to this guy to this guy. Okay. The example of well, I'm not coming up with an example. All right, so back to 3 bond areas. This is what we call trigonal planar. If you have a situation like ozone, and if you're curious, yes, I do like changing the colors. Ozone would have 18 electrons, 2, 4, 2, 4, 6, 7, 8, 9, 10, 11, 12. Ozone has only 3 electrons, 3 oxygens though. 2, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18. We do have a lone pair there. Count electrons, 2, 4, 6, 8, 2, 4, 6, 8, 2, 4, 6. So we have to double bond somebody. It doesn't matter who it is that's double bonded as long as somebody is. We could draw it like this, and it's the same molecule. And it's going to actually go back and forth. Okay, this is a bent molecule. We have 2 bonds, 1 lone pair. This is still trigonal planar geometry for the electrons, but the name of the molecule would be bent. So we talk about the geometry of where the electrons are, and then we talk about what the molecule shape's name is. And I know if I look, I can find, I just don't think I'll be able to write on it, but we'll find out. Come on, wake up. Here, we'll use the mouse. Maybe it'll be more responsive. This happens to be, I know right where it is because it's in here with the honor stuff. No, it's not. All right, you guys remember this? Yes, it's sideways. So I'm going to talk about it sideways. Turn your head sideways. Is this going to write on here? No, but you can see my cursor. Can you see the cursor, hopefully? Here is 3 bond areas. We've got trigonal planar and bent. Here's 4 bond areas. Here's 5 bond areas. Here is 6 bond areas. Oh, I know what I can do. Yay, now can I turn it? Can I rotate it? Yeah, look. I turned it upside down. There we go. Okay. So see how in this picture, there's 3 bond areas. So those are all trigonal planar. There's 4 here. There's 5 here. These are trigonal pyramidal. There's 6 here. Do you guys want me to show you how to count out 5 bonds and 6 bonds, or do you guys feel comfortable with that?
An example would be good.
Okay. Okay. So for the example for, oh, silly, PF5. Phosphorus has 5 electrons. Fluorine has 7. 7 times 5 is 35. So there's a total of 40 electrons here. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. We've got all of our fluorines on there. Now, why can we have 10 and not 8? Well, phosphorus, if we look at our periodic table, I think I actually have a periodic table app here. Yeah. Okay, if we look at our periodic table, phosphorus is in this third row. So you got hydrogen and helium in the first one, and the second one is lithium and beryllium and blah, 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 blah. And neon. The third one has sodium and magnesium, and then aluminum, and then silicon, and then phosphorus. Okay, so phosphorus is in the third family. Go back to yesterday when we talked about our hotel chart. The third family has d orbitals, doesn't it? They're not filled, but they're available, and that's important. That's why phosphorus and sulfur can have expanded valences past 8. Anybody in the second layer can only have 8, but anybody in the third layer on could go higher. So if you're faced with a picture of PF5, for instance, that tells you that, yeah, you can actually have 10 electrons around the phosphorus. Okay, another example, I'm going to look back at, I can get an example from here. All right, let's do ClF3. Chlorine has 7 electrons, each fluorine has 7, so that's a total of 28. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24. I have to go to 28 though, right? 25, 26, 27, 28. So let's count. I have 2 lone pairs and I have 3 bonds. That's a total of 5. So if we go back up here to the 5, I have 2 lone pairs, 3 bonds. The name of that guy is the T shape. Okay? Make sense?
Yes.
All right. If we do, we'll do xenon tetrafluoride. Eight for the xenon, and again, xenon will react even though noble gases don't react. He's got a big enough radius that it's easy to knock those electrons off, and fluorine's sexy. Always remember that. 28 plus 8 would be 36, so we have a total of 36 electrons. 2, 4, 6, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24, 25, 26, 27, 28, 30, 31, 32, 33, 34, 35, 36. We have 1, 2, 3, 4 bonds and 2 lone pairs, so that's a total of 6. So we're in this row, 4 bonds, 2 lone pairs is square planar. Okay? So once you've got it drawn, if you add up the number of bonds and lone pairs, you can figure out which one of these. Again, you're going to have access to your notes, so this might be a good thing to have out. Just a tip. Okay, now let's talk about why this is. We know how to draw them, we know how to name them, but why? Why do they make these shapes, and where are those electrons? Back to yesterday, we talked about orbitals. The s orbital is round. The p orbitals have that peanut shaped, and there's 3 of them. So here's S, P1, P2, P3. When an atom's by himself, this is the shape of the electrons. But as soon as they begin to bond, they change shape. And instead of having this goofy shape, we get a shape that looks like this. And then one that's going back into the board. So this is coming out, I'll make it darker, and this is going back in. What does that look like? That's tetrahedral, right? Just like this, tetrahedral. So this is an s orbital. There's a p, there's a p, there's a p. So these guys have what we call sp3 hybridization. That just means those orbitals have become Malumorphin Power Rangers and changed into the same size. Here we only have two, so we're using an S and two P's. There's still a third P in there, but he's unused. He's, if you think about it, if I drew these out so they're kind of in a plane instead of kind of standing up, the unused P orbital is sticking out perpendicular. Okay, that's important because that unused P orbital can double bond. Oh, no, that's not the way to draw it. Just, come on, erase. For some reason, we're really slow today. All right, these P orbitals, because they're sticking up here out of something, these guys can bond. There's the bond, the electrons that are being shared. And then you can have the double bond occurs up in here. So the way I would demonstrate it in class is I would shake somebody's hand and then I would take their other hand and go back and forth. And that was probably either Hayden or Brooklyn that always got it in third hour, and it was usually Elizabeth in second hour, because you guys were the ones that sat right in front of me when I lectured. So this is called a pi bond. That one's called a sigma bond. Okay, and that comes from what orbitals are overlapping. So we've defined the fact that the orbitals change shape. For trigonal planar, you have three orbitals in an unused p orbital that can be double bonded. That's why these guys are the only ones that have double bonds in them, or he can have double bonds. If you've got four bond electron areas, lone pairs and bonds, it's sp3. Now, there's only three p orbitals. So if we have, I'm going to switch back to a different color. Come on, computer. Now we can erase. Now it's stuck in erase mode. sp3, but we had to pick up one more orbital. Remember when I talked about yesterday, the d orbitals? That's why they can have those extra electron areas, because they use those d orbitals. So this guy becomes sp3d, and this guy becomes sp3d2. There's 4, 5, 6. 1, 2, 3, 4, 5, 6. Here, sp3d, there's 5. 1, 2, 3, 4, 5. All right, hit me. What kind of questions you got?
I think I'm good.
Okay.
I'm good on this right now.
Okay.
I'm good.
All right. Is that it on my list? Naming, shapes, hybridization, double versus single. All right, we got it all covered. I got this in video. Would this be helpful to have this particular printout?
Yeah, I mean, I don't see why Why not?
Okay, I'll figure out either how to share it or I'll cut and paste it so that you guys can have all the drawings, if the drawings make sense. All right. Anybody else have any questions about anything?
No, I talked to Piper and she said she has an appointment today and tomorrow, but I told her that the recordings will be sent out. So
Okay, good. Good. Well, and I can always one-on-one with somebody if you want me to. So if you have more questions, just call me, text me, call me, email me, whatever. I don't always check my email after I sit down at the sewing machine in the evenings though, so just in case. All right, any other questions? We're good?
good.
Okay, kiddos. Well, for the online lab thing, just do the first titration. If you want to do more, and I'd be happy to add it in for extra credit in somewhere if we need it, but you don't have to. Excuse me, I shouldn't be drinking Diet Coke while I lecture. Too many burps. Okay, kids. Well, stay safe. Tomorrow, 1 o'clock, we'll do quarter 3.
Sounds good.
Ta-ta. I gotta figure out how to get out of here.